In this video we introduce some important properties of the modulus and argument of a complex number. We start with a motivating example. So we have the complex number z has modulus 3 and argument 2. Complex number w has got modulus 5 and argument 1.6. So we have to express z and w in the p plus iq format. Now remember that if a complex number has modulus r and argument theta, then that means that z is equal to r times cos theta plus I sin theta. So that we can say that z must be 3, that's the modulus of z, times by cos 2 plus I sin 2, because 2 is the argument of z. And if we use our calculator and make sure that we're in radian mode, we get z is equal to minus 1.248 plus 2.727 times I. And similarly, we get w is 5 times cos 1.6 plus I sin 1.6, which gives minus 0.146 plus 4.997 times I. So we can now find z times w by multiplying together the answer for z by the answer for w. And again, if we use our calculators for this complex number calculation, we end up with z times w is minus 13.45 minus 6.64 I. So the modulus of z times w is going to be the square root of minus 13.45 squared add minus 6.64 squared, and that gives me 15 for the modulus of z times w. For the argument of z times w, it's well worth your while drawing a diagram again. So there's our diagram showing z times w, that is minus 13.45 minus 6.64 I. The argument of zw is this angle marked here, and to work that out we're going to first of all have to work out an acute angle using a little bit of right-angled triangle trigonometry. So our angle alpha there is tan to the minus 1 of 6.64 divided by 13.45. So the argument of zw is pi plus alpha, which is pi plus tan to the minus 1 of 6.64 divided by 13.45, which is 3.6. Now have a look to see whether you can notice any connection at all about the modulus of z times w and the argument of z times w and the initial modulus results and the initial argument results given at the beginning of the question. And moving on to z divided by w, well, z divided by w can be worked out on your calculator again, and that will give 0.552 plus 0.233 times I. So the modulus of z divided by w is going to be the square root of 0.5526 squared plus 0.2337 all squared, which comes out as being 0.6. And the argument of z divided by w in this case is easy because the point z over w is in the first quadrant. So the argument of z over w is simply the inverse tan of 0.2337 divided by 0.5526, which gives me 0.4 radians. And again, it's worthwhile just trying to notice any result or any connection between the modulus of z over w and the argument of z over w and the corresponding results for the modulus of z and the modulus of w, which were given at the beginning of the question. If the complex number z has modulus r and argument theta, and the complex number w has modulus s and argument phi, then we know that we can write z as being r cos theta plus I sin theta, and w can be written as s cos phi plus I sin phi. So z times w is the result of multiplying r cos theta plus I sin theta by s cos phi plus I sin phi, and that's going to give me rs times by cos theta plus I sin theta times by cos phi plus I sin phi. Now if we multiply out the double bracket, we're going to get cos theta cos phi plus cos theta times I sin phi plus I sin theta cos phi plus I squared times by sin theta sin phi. Of course, now I squared is minus 1, so when we multiply out the double bracket, if we collect together the real terms and the imaginary terms, we've got cos theta cos phi minus sin theta sin phi, and then we've got I times sin theta cos phi plus cos theta sin phi. Now, in the previous video we introduced the compound angle formulae, and you may have met them in your maths A-level studies as well. And the compound angle formulae tell me that cos theta cos phi minus sin theta sin phi is exactly the same thing as cos theta plus phi. Also tells me that sin theta cos phi plus cos theta sin phi is exactly the same thing as sine of theta plus phi. So our expanded version of ZW simplifies to RS times by cos theta plus phi plus I sin theta plus phi. Now we know that if we have a complex number with modulus r and argument theta, then the complex number is r times cos theta plus I sin theta. Now what we have here is we've got exactly that format, but we've, instead of the modulus just being r, the modulus now is rs, and instead of the argument just being theta, the argument part is now theta plus phi. So the result of multiplying z by w is to obtain a complex number whose modulus is rs and whose argument is theta plus phi. So we've got the modulus of zw is r times s, which is the same thing as the modulus of z times by the modulus of w. The argument of zw is theta plus phi, which is the same thing as the argument of z plus the argument of w. And we can express this in our shorthand version for complex numbers, which simply says that if we know that z has the form r theta, in other words z has modulus r and argument theta, and if w has modulus s and argument phi, then zw has modulus rs and argument theta plus phi. Now we can now move on and think about Z over W. Now if we have capital Z equals little z over little w, then that rearranges very quickly to tell me that little z is big Z times little w. So we can say that the modulus of little z must be the same thing as the modulus of big Z times w, and we know that that is the same thing as the modulus of z times by the modulus of w. And that straight away tells me that the modulus of z is the same thing as the modulus of little z divided by the modulus of little w. What's more, we know that the argument of little z is the same thing as the argument of big Z times w. So that is the argument of big Z plus the argument of little w. And that rearranges to tell me that the argument of big Z is the argument of little z, take away the argument of little w. So we have now got the two results, that the modulus of z over w is the modulus of z divided by the modulus of w, and the argument of z over w is the argument of z minus the argument of w. And again, we can express that using the shorthand notation. So to summarise, we've got the two results for modulus, and we've got the two results for argument. Modulus ones are very intuitive. The argument ones, a little bit less so. And if you think about it, argument is behaving like logarithms. And there is in fact a very close connection between the argument and logarithms, which you might discover later. When we're using the argument result, we do need to be careful that we remember any conventions that are being used in the question about argument. So for example, if the convention being used is that the argument should lie between 0 and 2 pi, and we know that the argument of z is 3 pi by 4, and the argument of w is 11 pi by 6, then we can say that the argument of z times w must be the same thing as the argument of z plus the argument of w. So that's 3 pi by 4 plus 11 pi by 6, which gives me 31 pi by 12. However, 31 pi by 12 is more than 2 pi, so it's not in the domain, or the range rather, of values that we allow for argument. So we need to give it a little bit of thought. And if we think about an angle of 31 pi by 12, that is a full rotation of 2 pi plus an extra 7 pi by 12. So what we need to do is we just need to ignore that full circuit of 2 pi and say that our argument of 31 pi by 12 can actually be rewritten rather better as just 7 pi by 12. So rather than leaving the answer as 31 pi by 12, we'd write the answer as 7 pi by 12. So to finish with, we've got an example. Complex number z has modulus 4 and argument 2 pi by 3. Complex number w has modulus 5 and argument 7 pi by 4. We're going to find the modulus and argument of zw, w over z, and z over w. Now, we have an argument of 7 pi by 4, and that is between 0 and 2 pi. It certainly isn't between minus pi and pi. So in this question, the context of the question is making it quite clear that arguments are being given as angles between 0 and 2 pi. So starting off with z times w then, the modulus of zw we know is the same thing as the modulus of z times the modulus of w, so that's simply 4 times 5, which is 20. The argument of z times w is the argument of z plus the argument of w, which is 2 pi by 3 plus 7 pi by 4, which comes out to be 29 pi by 12. Now 29 pi by 12 is more than 2 pi. So what we've got to do is think of 29 pi by 12 as being 2 pi plus an extra 5 pi by 12. And we can forget all about the 2 pi and say that that simplifies to an argument of 5 pi by 12, which is within the range of values that we're looking for. For part B, we want the modulus and argument of w over z. Well, the modulus of w over z is the modulus of w divided by the modulus of z, which is 5 over 4. The argument of w over z is going to be the argument of w take away the argument of z, which is 7 pi by 4 take away 2 pi by 3, which is 13 pi by 12. We've no problem with that because that is certainly between 0 and 2 pi. For part C, we have the modulus of z over w is the modulus of z divided by the modulus of w, which is 4 over 5. The argument of z over w is going to be the argument of z minus the argument of w, so that is 2 pi by 3 take away 7 pi by 4, which equals minus 13 pi by 12. Now we're only allowed arguments between 0 and 2 pi, so we can't have an argument of minus 13 pi by 12. An argument of minus 13 pi by 12 means that we've got to go 13 pi by 12 in a clockwise direction from the positive real axis. And going 13 pi by 12 in a clockwise direction is the same thing as going 11 pi by 12 in an anti-clockwise direction. So the argument of z over w can be written as 11 pi by 12. And that concludes our introduction to the properties of the modulus and argument of complex numbers.